So we need to differentiate the Taylor series centered at 0 for the given function. We also need to identify the function represented by the differentiated series. And finally, we need to give the interval of convergence of the power series for the derivative. So the function which is given for the Taylor series is f of x. So let's do part 8. Here is the Taylor series for f of x centered at 0 is 1 over 1 minus x equals 1 plus x squared plus x cubed plus x to the 4th power and so on. So it equals the sum from n equals 0 to infinity of x to the nth power. Now we will differentiate this series with respect to x. So the derivative of 1 plus x squared plus x cubed plus so on with respect to x equals 1 plus 2x plus 3x squared plus 4x cubed and so on. So this equals, we can rewrite this as the sum from n equals 1 to infinity of n times x to the power of n minus 1. So now we will do part b. To find the function represented by the differentiated series, we differentiate f of x. So f prime of x equals the derivative of 1 over 1 minus x with respect to x. So it equals 1 over 1 minus x squared. Therefore, this is the function represented by the differentiated series, and we can call it, for example, h of x. So h of x equals this. Wait, let me highlight it. Okay, and part C, now we need to find the interval of convergence of the power series for the derivative. So the power series for the derivative is f prime of x equals the sum of from n equals 1 to infinity of n times x to the power of n minus 1. We will use the ratio test to compute the interval of convergence. So limit of absolute value of a n plus 1 over absolute value of a n where n approaches infinity equals limit of n plus the absolute value of n plus 1 multiplied by x to the nth power over the absolute value of n times x to the power of n minus 1 where n approaches infinity, and this equals limit of n plus 1 over n multiplied by the absolute value of x where n approaches infinity, and this equals the limit of n times 1 plus 1 over n times the absolute value of x. This equals the limit of 1 plus 1 over n times the absolute value of x, and finally this equals 1 plus 0 times the absolute value of x, so it equals the absolute value of x. So the series converges for absolute values for the absolute value of x less than 0. So converges for the absolute value of x less than 1. So that means that x is larger than negative 1 but less than 1. Now we have to check the convergence of series at the endpoints of the interval. So at x equals negative 1, the series becomes the sum of from n equals 1 to infinity of n times negative 1 to the power of n minus 1, as limit of an where n approaches infinity does not exist. Therefore, by the series divergence test, the series diverges. So diverges. And now let's check at x equals 1. The series becomes the sum from n equals 1 to infinity of n times 1 to the power of n minus 1. And it equals the sum of n from n equals 1 to infinity. So as limit of an, where n approaches infinity, equals infinity here, the series also diverges here. So diverges. So that means that the interval of convergence